We're going to look at the electric potential due to point charges. This is going to be a pretty quick video because we've talked about electric potential in the last video, but what we haven't talked about is how it works when you're talking about point charges. For instance, if I have a positive charge, it's going to create an electric field. And that electric field will have different points of potential because the electric field strength varies from point to point. So unlike in the last video, because we don't have a constant electric field, we also don't have constant forces. So if I have point A here and point B out here, the amount of work done in moving a charge from A to B or B to A is not something that you can use this formula for. This formula only worked when the electric field is unchanging. The electric field being kq over r squared, we would find that the electric field would be stronger closer to the charge and weaker as you go further out. So the amount of force that you use in moving this from A to B is going to change as you move it. Now, when you get yourself in a situation like that, the only way to deal with it is to do some calculus. And we're not a calculus-based class, so I'm just going to show you the result of that. And the result of that is that the voltage potential difference in this situation is kq over r. And you'll notice that the r is no longer squared. What that means is that if I know the q refers to the charge that's creating the field, of course, and r is the distance away. Now, since it's a potential difference, often we would be doing something along the lines of this. And since we have two r's, we would say that if we're moving from A to B, we would be putting the distance from the charge for B and the distance to the charge in the center for point A. The reference for this, this is what you would do if you were given two different points in space. So the situation we're most likely to deal with would be a situation where we have a charge here. I'm not going to draw the field lines again, but you know they're there. And we're going to have a point out here, which we'll just call P, point P. And we want to know the amount of potential at that point compared to where it has none. Remember, when we did these kind of problems for gravitational potential energy, we would say, hey, the ground is 0, and then we want to know the potential energy at some place higher than that. Here, we also want to reference how much potential do we have compared to where it's 0. But for a charge, 0 is going to be when r is all the way out at infinity, because if you put infinity into this equation up here, E goes to 0. E is 0 when r is infinity. If we're going from infinity to there, if we cross this out and replace that with an infinity, anything over infinity is 0. So we just get right back to where we started, which is that the voltage difference relative to infinity is kq over r. And the infinity part is generally implied. Okay. That's a lot of technical stuff. So let's use this formula. It's not that hard, so we're going to do a couple of examples. Okay, our job is to find what the potential is due to this 20 microcoulomb charge at a distance of 0.50 meters away. So we're just going to use our formula kq over r. Plugging the numbers in, we're going to have 9 times 10 to the 9 for k. The q is 20 times 10 to the negative 6 coulombs over a distance of 0.50 meters. Calculator says that comes out to 3.6 times 10 to the 5 volts. So there would be a 3.6 times 10 to the 5 volt potential associated with this position. If I put an entire coulomb of charge there, it would have a potential energy of 3.6 times 10 to the 5 joules. Let's do another example. Alright, what minimum work must be done by an external force to bring a charge of 3 microcoulombs from a great distance away to a point 0.500 meters from a charge of Q equals 20 microcoulombs? So we have a charge here of 20 microcoulombs, and we're trying to bring a charge from very far away, from a great distance away, aka r equals infinity. That's how they'll say things like that often in these problems, to a point that is 0.5 meters away, right? And the amount of charge we're going to bring, this little charge that we're going to bring to that point from far away, is 3 microcoulombs. The way to do this is just to figure out what the voltage potential is here at this point right here, and recognize that the potential energy is going to be, the work done, I'm going to write this up here, is going to be equal to the change in potential. So if I'm doing work, I'm giving this thing potential energy. So that change in potential energy will be the charge that we bring to that point times the voltage associated with that point. So what we have to do is then find that voltage, and then we'll just multiply it by the charge. So the voltage is going to be kQ over R. Now this Q is the charge that is making the electric field and that the potential is relative to. So this Q, even though I wrote a little q, is the big Q over here. So we're going to put that number in. So we're going to have 9 times 10 to the 9 times 20 times 10 to the negative 6 coulombs over that distance of 0.5 meters. Okay, let's see what that comes out to. Hey, what do you know? It's the same answer as in the previous problem. That's probably because it's the exact same numbers that were in the previous problem. What serendipity. Alright, so we've got 3.6 times 10 to the 5 volts. And now to find the potential energy change, which is equal to that work, we're going to multiply that by our charge of 3 times 10 to the negative 6 coulombs. And I'll write this out to the bitter end, and then start, and then I will put it in the calculator. And that comes out to 1.08 joules. Now, another type of problem you could come across would be very similar to the kind of problems we had when we were doing electric field. Let's say you had a charge over here, Q1, and a charge over here, Q2. And you were supposed to find the net voltage in this position somewhere in the middle, or it could even be somewhere over here. It doesn't matter where. But what we'd have to do is we'd have to use our formula. And when I say the formula, I mean the one up here, because these are point charges. I'd have to use that formula twice, once for each charge and each distance. So we'll call this R1 and R2. Now here's where it gets different than what we did with electric fields and electric forces. Voltage is not a vector. When I find the voltage due to charge 1 and I find the voltage due to charge 2, I will simply add them. So the voltage total would just be V1 plus V2. They're not vectors. Now, if one of these is negative, because say one of the charges is negative, then that'll be a negative number and they will subtract. But it's not because they're vectors, it's just because you've got a positive one and a negative one. Alright, good luck.